Today, I'm going to teach you about continuity, explaining what it means for a function to be continuous at a point on an interval, what continuity is in general, and what it means to have a discontinuity on a line. Now, by the end of this video, we're going to be able to discern on what intervals this graph on screen is continuous. So, say from x equals 2 to x equals 4, is this continuous? And hopefully pick apart different kinds of discontinuities as well. So first we're going to look at the definition of continuity, like what even is it? For a function to be continuous at some point x equals c, it must satisfy three conditions. So right now we're just talking about a point, not an interval. The first condition, f of c has to exist. There has to be some value of y that corresponds with the value of x. So there can't be a hole, there can't be a vertical asymptote, there has to be a point. Next, the limit as x approaches c of f of x must exist. So the limit at that same point has to exist. There can't be any kind of jump. There can't be limits that are different from either side. And finally, f of c must equal the limit as x approaches c of f of x. So whatever value you get here, you have to compare it to the value you get here. And if they're the same, the function is continuous. And if they're different, the function is not continuous. So if any of these conditions are not met, the function is not continuous at that point and has a discontinuity. So first, we're going to try this example, which asks, is f of x equals x cubed continuous at x equals 0? And here we have the graph of f of x equals x cubed, just so we can reference it. So we need to try each of these three conditions and see if they apply, because only if all three are true, again, can we say it's continuous. So first, we're going to see if f of 0 exists. Plugging in 0, we would get 0 cubed, which equals 0. So first check. Next, we're going to take the limit as x approaches 0 of x cubed. And you can see at this graph, if we go from the left, we approach 0. If we go from the right, we approach 0. Also, using the plug-in method, we would get 0 cubed, which is 0. So this is also 0. So the limit does exist, but now as for the final test, we're going to see, does f of 0 equal the limit as x approaches 0 of x cubed? And we will see that both of them are 0, so this is in fact true. So because all three conditions are met, x cubed is continuous at the point x equals 0. Next, we're going to figure out whether f of x is continuous at x equals pi over 2, where f of x is given by this graph. Now, although we don't know the equation for f of x, we can use the information from this graph to figure out whether this function is continuous at this certain point. Now, first, we need to figure out whether f of pi over 2 exists. So we're going to go ahead and look at this graph and see whether there's a y value that corresponds to x equals pi over 2. Although there is a hole here, you might be inclined to say, well, it doesn't exist at this point. There actually is a y value that corresponds with x equals pi over 2, and that is y equals 1.25. You can see here through this point. So you can see here, this is an instance where it may not seem like a value exists, but it actually does. Next, we're going to see if the limit as x approaches pi over 2 exists. And although we don't have any equation we can use, we can't use any algebraic methods, we can simply look at the graph and see whether this limit exists. So if we go from the left, we can see that this curve is approaching y equals 1. And if we go from the right, it's also approaching y equals 1. Again, it doesn't matter if there's a hole, the limit can still equal 1. So we're going to get that this limit equals 1. And now for the final test. So far, so good, but if it doesn't meet this last condition, we may not have a continuous point. Are these two equal? Well, we can see that 1.25 does not equal 1. So the third condition is not met, and therefore f of x is not continuous at x equals pi over 2. And so we can see this is a clear example when maybe some of the conditions are true, but not all of them. So again, you need all three conditions to be true for it to be continuous. And we're actually going to explore this idea of not being continuous by looking at different kinds of discontinuities you may have. So the first kind of discontinuity we're going to look at is what is called a jump discontinuity. Now, as you can see here, we look at two lines which are disconnected from each other, and you can see that the function kind of jumps at this point and isn't connected. So here we're breaking rule number 1, 2, and 3. We don't have any value which exists at this point. The limit from the left does not equal the limit from the right, so the limit doesn't even exist. And then, of course, if the limit doesn't exist, the point doesn't exist, there's nothing to do about the third condition. Now, the next kind of discontinuity that you might see is vertical asymptote discontinuity. This is simply just whenever you have a vertical asymptote, which causes the function to not exist at a certain point, and therefore violate the first condition of continuity. And you can kind of visualize continuity in a way, because you can see here that the line isn't connected. It's not a continuous line. So just looking at this visually, it kind of makes sense that this isn't continuous because the lines disconnect and go on to infinity. And now the third type of discontinuity is a removable discontinuity. Now, we saw a similar case in the last example where the first two conditions of continuity are met, but not the third. So we have a limit which exists, we have a y value to match this x value, but because the two don't match up, it's not continuous. And what's interesting about removable discontinuities is that you can actually modify the function and turn it into a continuous point so that it becomes continuous. And we're going to figure out how to do that later, but essentially you just move this point into the place of the hole and make it continuous, which is why it's called removable discontinuity, because it's possible to remove the discontinuity altogether. So now we're going to go into what it means to be continuous on an interval. Essentially, a function is continuous on an interval if it's continuous for every point on that interval. And the easiest way to determine continuity on an interval is just to move from left to right and stop once you reach a discontinuity. So, starting from x equals 0, we reach x equals 1 when we see that we have a jump discontinuity. So we're just going to go ahead and label this. We're going to say continuous on, and then the way that you write an interval is using brackets and parentheses. Brackets means that the interval is inclusive, and parentheses means that it is exclusive. So because the function exists at x equals 0, we're going to put a bracket, 0, because the function is continuous at x equals 0 as well. It includes 0. But then, once we reach 1, we're going to put a parentheses, because the function is not continuous in this point. It is exclusive. So now that we've established this interval of continuity, we're going to move on to the rest of the function. Again, we're going to move left to right. So right off the bat, we can say that we're going to have a parentheses for x equals 1. And this little u thing is just to connect your different intervals. That's the notation you're going to use. So back to the graph. If we keep moving right, we eventually reach a vertical asymptote, which was the second type of discontinuity we learned. So because a vertical asymptote means it's not continuous, that means that once we get to x equals 5, we're going to put a parentheses to show that continuity does not include x equals 5. So when it comes to determining continuity on an interval, you just need to make sure that every point on that interval is continuous. And if the boundaries of the interval are not continuous, then you need to make sure you specify that with parentheses. So we're basically just scanning this graph until we find a discontinuity, and then starting a new interval from there. Now we're going to practice this again with another example in which we need to find on what intervals g of x is continuous, and then after we do that, we're going to try and remove the discontinuity at x equals 5. But starting with the first part of the question, we're going to again scan from left to right. And we immediately see that there is a vertical asymptote at x equals 0. So right off the bat, we're going to start off our interval with an open parentheses, 0. Because again, the function is not defined at x equals 0 and therefore is not continuous. Moving on, we keep going right until we reach the hole at x equals 2. Because the function is undefined at this point, as there is no y value corresponding with x equals 2, that means the first condition of continuity is violated, and therefore this interval of continuity stops at x equals 2. Open bracket, because it is not continuous at x equals 2 specifically. We're going to keep moving. We can go right pretty far until we reach this removable discontinuity here. Again, this function is not continuous at x equals 2, nor is it continuous at x equals 5. So we can go ahead and put an open parentheses. And then our final skim, we keep moving right, and the function is pretty much continuous from this point on. So we can actually use closed brackets around the 6 because there is a limit for this point, and it has an existing y value which matches up with that limit. So this would be our interval of continuity, and you can see that the key here is recognizing different sources of discontinuity. Here we saw there was a vertical asymptote, here we recognized a hole, and here we recognized a removable discontinuity. And on the subject of this removable discontinuity, we're going to figure out how we can actually remove it and make the function continuous at that point. So what we're basically going to do is take this point and move it downwards so that it takes up the space of the hole and makes this one continuous line. Now, in order to do this, we're actually going to use a piecewise function, which I'm going to name p of x, and I'm going to just move it down here so we have extra room. Now, this new function is going to use two components. First, we're going to leave g of x as normal, except for at x equals 5, because that's where the discontinuity we want to remove occurs. So we're just going to say g of x is exactly as it was, except once we reach x equals 5, maneuvering around x equals 5, as you can see here. And note that we're using a less than sign and not a less than or equal to, because the function does not exist at that point, so we can't say that it's an inclusive boundary. Now, we need to figure out what y value we want to change this point to. And because this hole is located at y equals 1.25, as you can see here, that means we're going to establish that this new function equals 1.25 at x equals 5. And if you don't understand this because of the confusion of piecewise functions, I can make another video on this too. Just let me know in the comments below, but if you're familiar with piecewise functions, you should understand what we're doing here. So essentially, we're stating that we have a new function now, which is exactly like this regular g of x we have, proceeding as usual until we reach x equals 5, when we've now defined a new point right here, and then right here you can see we've still said g of x proceeds as usual until x equals 6. And our new function that we've written as p of x, you can see that it is now continuous at x equals 5, because g of 5 exists and equals 1.25. The limit as x approaches 5 exists and also equals 1.25. So therefore this function is now continuous and we have successfully removed the discontinuity. So now that we've learned what continuity is and how to determine it on an interval, we can move back to this problem from the beginning of the video and use our knowledge to solve it. So if you'd like to pause the video now and write down the intervals of continuity for this function, you can go ahead and do that now. Anyway, we're going to start off by using the left to right method. Starting here, we can see that it is continuous at x equals 0 because f of 0 exists and the limit exists and equals f of 0. So we're going to start this off with a closed bracket with 0. Now, moving left to right, we reach our first discontinuity at x equals 2, where we have a hole, so we're going to go ahead and put 2 with an open parentheses. Continuing on, we reach our next discontinuity at x equals 4, where we have a vertical asymptote. So we can go ahead and write open parentheses 2, comma, open parentheses 4, as there is no value at x equals 4, so it is not continuous at that specific point. Moving forward, we reach our next discontinuity at x equals 5, where there is a jump discontinuity. Again, we're going to use 2 open parentheses because the function is not continuous at any of these endpoints. And then lastly, we can see that moving left to right, there is no other point at which the function is discontinuous because it moves on to infinity, as shown by this arrow. So therefore, the last interval is going to be 5, infinity. Now, here, we need to make sure we use a parentheses instead of a bracket, because infinity is not a number you can quantify and is therefore not included in this interval. So you never want to put a bracket around an infinity. Or a negative infinity for that matter. This is incorrect. So we want to make sure when we have infinity or negative infinity, we put a parentheses. But other than that, this would be the interval of continuity for this function. I hope you guys enjoyed this video. Leave in the comments anything you're still confused on or which I can make another video on. And if you learned something from this, make sure to like and subscribe, and thank you.